Okay, well, we'll begin, and yes, happy Friday of ninth week. Just a few more days left. So today we will talk about statistical inference. For numeric variables. And there's technically 4 topics here, and I think we'll get through 2 of them today, and we'll finish the other 2 on Monday. These 4 topics, which are kind of laid out for you on the formula sheet, we've got confidence intervals, for mu based on one sample. And then we've got confidence intervals for the quantity mu1 minus mu2 based on 2 samples. We have hypothesis tests for mu based on 1 sample and hypothesis tests for mu1 and mu2 based on 2 samples. Okay. And we've pretty much covered the equivalence of these, but for proportions when we were dealing with categorical variables. So when we had categorical variables, we dealt with proportions. It would be things like the proportion of people that have a cat, okay, and that's a category. You either have a cat or you don't, okay, or the proportion of M&Ms that are red. The M&M is either red or it's not, or, you know, those are categorical variables. Now we are dealing with numeric variables. Numeric variables will be things like the height of someone, or, you know, the weight of an animal, or, you know, some kind of numeric variable. And the question that we're asking now is not about the proportion of the sample, but about the mean of the sample and what the mean of the sample has to say about the mean of the population. Some of you guys came in a little bit late. I've got papers for you to pick up, formula sheets, so you'll have to come back and grab them. So, okay, so we do inference about the mean of the populations. Okay, so now that we have a numeric variable, we are talking about the mean. A very important part about this is that the homework, I mean not the homework, but the test problems will not say this is dealing with numeric variables or this is dealing with categorical variables. You have to figure that part out yourself, okay? So, very important. Okay. You must figure out for yourself you know, if you are dealing with a categorical or numeric variable. And so this goes back all the way to our first week of class when we talked about what's a categorical variable, what's a numeric variable. If it's categorical, Categorical means you are dealing with proportions. Proportions P. And you will use the z-table. When you are dealing with numeric variables, you will be dealing with means, mu, and you will always use the t-table. Okay. And so I passed out t-tables on Wednesday, and we'll take a look at the t-table today, showing you how to use all of that. Now, probably in today's lecture, I'll get through these first two. I don't think we'll have time for the third one, but basically, if you understood confidence intervals when we were dealing with proportions, then you'll understand confidence intervals when we're dealing with means. It's the same basic concepts, it's just the formula for the standard error has changed, and instead of the z-table, we're using the t-table. Okay, so first we'll deal with the confidence interval for means with one sample. And let me just do a quick review. Recall the confidence interval for P. Okay. When we created the confidence interval for P, what goes in the middle? P hat, right? P hat plus or minus what? Z star times the standard error. Okay. And so I just kind of want to label each of these things. P hat serves as, this is our best guess for P based on the data. Okay, this serves as the center of our interval. Okay, and then this Z star is our critical value, and we have the standard error. Okay, the standard error acts as kind of our estimate of the standard deviation of the sampling distribution, right? Okay. Now we're going to make the confidence interval for mu based on the sample, okay? Okay, it's going to have the exact same structure, except our best guess for mu based on the data, which goes in the center. What do you think our best guess for the population mean is? The sample mean, right? So we're going to put x bar in the middle. Then we will go plus or minus. Instead of z star, we're dealing with the t-table, so we'll have t star multiplied by the standard error, okay? And so x bar serves as our best guess for mu instead of p, for mu based on the data, and this will be our center. T star is our critical value. This comes from the table. And here we have the standard error. So it's pretty much exactly the same. The only thing that changes now is the way we calculate the standard error is going to be using the formula S divided by the square root of n. Okay? What is S? S is the sample standard deviation. And n is our sample size, as always. Okay. The way we take T star, though, T star comes from the T table. And we need the confidence level. So whether we want to be 90% confidence, we need confidence level, and we need something called degrees of freedom. Okay, and we abbreviate degrees of freedom as DF, and DF is equal to n minus 1, one less than our sample size. The concept of degrees of freedom is based on the idea of how many numbers are free to vary if you have a set sample mean or something. So for example, I could say we can play a game where we're going to pick 10 numbers, and I can guarantee that the average of these 10 numbers is going to be 100. Okay, whatever numbers we pick, I can guarantee that the average of these 10 numbers is 100, as long as I get to pick the last number, right? So you guys can pick 9 of the numbers, and then I just have to pick the last number so that when we add all 10 numbers together, it adds up to 1,000, right? And if we do that, I can guarantee that the average is 100. And so in that concept, if we're going to have 10 numbers in our sample, 9 of those numbers are free to vary, and the last one, I have to pick to guarantee that it'll equal 1,000. So that's kind of where this idea of degrees of freedom being n minus 1 comes from. That's like a very loose illustration. It's not the formal mathematical definition there, but just to kind of give you an idea of why this thing is called such a thing. That's what we have, okay? And so with degrees of freedom and the confidence level, basically you just go to your t-table, which should look like this, and let's say we have a sample of 10, we would have 9 degrees of freedom, and if we're going to make a 95% confidence interval, then our t star is going to be, you go down the 95% column, and you go to 9 degrees of freedom, and the t star that you would pick is 2.262, okay? You guys see that on your table, I hope? All right. And then you'll actually notice that if you go all the way to the bottom with infinity degrees of freedom, it becomes the same values as your z star. So I think I gave you 4 z star values. I said 95% you use 1.96, and 90% you use 1.645, and things like that. They actually have a third decimal, so it's 1.282 and 2.576 rather than 2.58, but close enough. But anyway, just use the degrees of freedom and your confidence level. Okay, so let's just try out a quick example here, and we will say, we wish to estimate the mean earnings, or we'll say, yeah, the mean weekly revenue of a vending machine. I don't know. This is something stupid. Okay. And so what we can do is maybe we select 12 random weeks. Okay, and then we measure the revenue, and we will say during the 12 weeks, the mean revenue is, I don't know, $146 with a standard deviation of $18. Okay. So during those 12 weeks, we average 146 with a standard deviation of 18. Okay, so we'll say make a 90% confidence interval for the revenue. And I will say the mean revenue up in the population. So the population would be all weeks, right? All. Okay, I'll just do this. Okay. So we got x bar plus or minus t star times the standard error. Okay, and the standard error is equal to s divided by the square root of n. Okay, so we're going to go through, I'm going to just label kind of the values that we have. 12, this is equal to what? What value is this? This is n, right? Okay, 146, this is x bar, 18, that's s. Okay, so I've got 146 plus or minus. Okay, for t star, what do we have? We got 90% confidence. How many degrees of freedom do I have? N minus 1, I've got 11 degrees of freedom. So I go to the table, I go to 11 degrees of freedom. What did I say, 90% confidence? 90% confidence, 11 degrees of freedom. The value I'm going to use, 1.796. So my t star is equal to 1.796. Okay, so I got 146 plus or minus 1.796 times s being 18 divided by the square root of 12. 146 plus or minus 18 divided by the square root of 12 times 1.796. Okay, 146 plus or minus 9.33. Okay, so this gives me on the low end 146 minus 9.33, 136.67, and on the high end 155.33. All right, and I would say something like, I am 90% confident that the average revenue per week is between 136.67 and 155.33. It's not too bad, right? This is my 90% confidence interval. Okay, so we'll just do a few quick questions. I guess we can make this quicker question. So I could ask, does our confidence interval provide evidence against the claim that the average earnings or average weekly revenue is, let's see, let me get this software running. We'll say is 140. Okay, and so your answer choices are yes, A, and B is no. There we go. So we're going to click start a session. All right, I mean, this should be easy, right? I hope. So if we understood confidence intervals for proportions, it's all the same here. Okay, is this running? Okay. Oh yeah, great. And everybody is clicking away. So does our confidence interval provide evidence against the claim that the average weekly revenue is 140? Okay, did we all get our clicks in? Okay, I'm going to go ahead and click stop here. Okay, and yeah, okay. Somebody clicked E, I don't know. Okay, well. Yeah. Okay, so yeah, you guys got this. Okay, and then so if I said, do we have evidence that the mean is 140? You would all say what? You would also say no, because confidence intervals. Well, okay, so I'm sorry. So the answer here is no, and you guys all knew that because 140 is in the interval, so it's plausible. Okay, and then no, confidence intervals do not provide evidence that, mu is equal to some specific number. Okay, and then the other question could be, does our confidence interval provide evidence against a claim that the average weekly revenue is, and then we put in some number outside of the interval, and you would say, yes, we have evidence that it's not that value, right? I'm just going to copy and paste the text here, and then just change it to, whoops. I'm going through this quickly because I'm hoping we're all very comfortable with this stuff. So I'm gonna put like 180, and then we say yes, 180 is not in the interval, so we have evidence against it. Okay. All good? All right, so then we'll just keep chugging right along. So on the formula sheet, I guess I'll just highlight this. Okay, well, first of all, with the formula sheet, we did not cover confidence intervals, proportions, two samples. You can put a little X through that if you want. You can just you can do this just for this, okay? The other stuff we have done, okay? And so, this shows the formulas for confidence intervals for proportions p hat plus or minus z star times the standard error. P hat is this, the standard error is this, and the z stars are these four values, okay? And then with hypothesis tests, it says, these are your hypotheses, these are the values you have, and then, here's your standard error and all of that. Okay, and here we're talking confidence intervals for means, one sample, x bar plus or minus t star times the standard error, and standard error is s divided by the square root of n, and then it says t star comes from the t table with degrees of freedom equal to n minus 1, and then yeah, well, for two samples use the smaller of n1 and n2 as n, so it's all kind of there. You just have to know how to use the results of the confidence interval, right? Okay, so we'll take a look at confidence intervals for means with two proportions. So this is a confidence interval for mu1 minus mu2 based on two samples. Okay. And here the idea is we are trying to create a confidence interval for the difference. Okay, so this is a little bit different. So we make a confidence interval for the difference between the mean of population 1 and the mean of population 2. Okay, and so just for example, just to kind of imagine what this confidence interval should look like, let's say we are looking at the heights of men and the heights of women, okay? And so we'll just say population 1 will be men, and population 2 will be women, okay? And or anyone, this can just be self-identified men and women, and we will look at the mean height. So mu1 will be the mean height for men, and mu2 will be the mean height for women. All right, and I'll just tell you, in the U.S., mu1, whoops, something happened. Okay, in the U.S., mu1 is, is around 70 inches, 5'10", 5'9.5", something around there. And mu2 is something around, I'm just saying, 5'4", 5'5", we'll say 65 inches, something around there, okay? 5'4", 5'5", something around there. Okay, so what we want to do is we want to create a confidence interval for the difference, okay? So, kind of what do you think the, what is kind of the order of magnitude, or what kind of ranges will we see for the confidence interval for the difference? Do you think we're going to see differences like, from 65 to 70, from 20 to 30, 10 to 15, 4 to 8? What kind of difference do you think we'll see here? Okay, so I'm just making up numbers, but a reasonable confidence interval for mu1 minus mu2 might be something like 3.5 to 6.5. Or, we can just say 3 to 7 or 4 to 6, something around there. And what this is this is the difference between the average height of men and the average height of women. If we could imagine that there existed such a thing as the average man and such a thing as the average woman, okay, just some hypothetical concept here. The question here is, how much taller is the, quote, average man than the average woman? And we would say, based on the data we've seen, we would guess that the average man would be somewhere in between 3.5 to 6.5 inches taller than the average woman. Okay, if we'll play along and say such a thing, we can imagine such a thing. Okay, so this would be it's kind of like the answer to the question, how much taller is the, quote, average man than the, quote, average woman? And we would say, we would estimate something between 3.5 to 6.5 inches taller. And we are only talking about the mean of population 1 and the mean of population 2, okay? We're not talking about individuals. If we were to pick an individual man and an individual woman, those individuals could have drastically different height differences, right? We could have a woman who is very tall and a man who is short, or vice versa. And if we just picked a random individual man and a random individual woman, difference could be anywhere from, you know, whatever to whatever, okay? You could have a negative difference to a very positive difference. That's not what we're talking about. We're talking about the average of population 1, which in this case would be the mean height of men, and the average of population 2, in our case, the mean height of women, okay? And so this is the interval that we are creating, okay? All right, so as far as the formula goes, okay, we're making a confidence interval for the quantity mu1 minus mu2. So what do you think will go in the middle? In the middle, we always put our best guess for what mu1 minus mu2 is, right? What would the best guess for mu1 minus mu2 be? It's going to be the difference between x bar 1 and x bar 2. Okay, that's going to be our best guess. That goes right in the middle. And then we do plus or minus critical value t star times the standard error. Okay, the standard error just has this formula, slightly complicated, but not too terrible. S1 squared divided by N1 plus S2 squared divided by N2. And that's it, okay? The degrees of freedom for T star, you know, you look up, you need the confidence level and degrees of freedom. Degrees of freedom is still n minus 1, but now we have two n's, okay? Okay, we have two n's, so what we do is we use the smaller value between n1 and n2. We have two n's, so we use the smaller of n1 and n2. Also, with picking your degrees of freedom, sometimes you won't find your exact degrees of freedom in the table. And what we do is, just to be safe, we pick the smaller degrees of freedom. Okay, we always round down. Okay, if you do not see if you can't find the exact degrees of freedom, always round down to be safe. Whatever safe means in the context of statistical inference. Well, what safe means in the context of statistical inference is that our interval ends up being a little bit wider than perhaps it needs to be, right? Wider intervals generally correspond to us being a little bit more confident about capturing the true value of mu in there. Okay, so we'll try another example here. And I'll take a look. Okay, so let's say we wish to create a confidence interval for the difference between the, I don't know, mean weight of, what do we want to do? We'll do golden retrievers. How much do golden retrievers weigh? Golden retrievers and Labrador retrievers. These are like the two most popular breeds of dogs in the US, at least. I don't know about other nations. Do you think German Shepherds are more popular in Germany than, I don't know. Okay, well, let's see. All right. Average weight of a golden retriever. Okay. This makes it complicated. Okay. So according to Google, we'll for golden retrievers. Okay, so we'll say sample 1 will be the Goldens, and we'll say the mean of sample 1 was, we'll say 70. The standard deviation we'll put at 4, and we'll say we took, let me throw in some decimals here. So 70.3, 4.2, and we'll say we took a sample of 15 golden retrievers. I guess I'm kind of making it too easy. Probably your values will come in text form, okay? And we'll say, you know, so I'll just do this for the other side, but it's easy, right? So we'll say we took a random sample, let's say of 13 Labrador retrievers. Okay, the mean weight in this sample is, okay, oops, average weight of a Labrador retriever. Okay, and the mean weight here is, we'll say, what is this? I can't do math. We'll say 63.8 with a standard deviation of 7.9 pounds. Okay. And so we're going to ask, make a 95% confidence interval for mu1 minus mu2. Okay, so you know, probably your values will come in text form, and so you just have to go through and you label these. And so we're going to call this sample 1. So this will be x bar 1, this will be S1, and this is N1. And then I would just go through and I would label each of these things. So 13 is N2, 63.8, this is x bar 2, and standard deviation 7.9, this is S2. Yeah. All right, so I go through x bar 1 minus x bar 2 plus or minus t star times the standard error. Okay, this gives me, we'll plug in our values. Oh wait, and then let me just say standard error is equal to S1 squared over N1 plus S2 squared over N2. Okay, so we'll fill in these values. S1 squared over N1 is 4.2 squared over 15 plus 7.9 squared over 13. My standard error, when I punch this into the calculator, make sure you know how to use your calculator, okay? I mean, it's not, you laugh, but sometimes this is the thing that causes issues on the test, and we don't want that to be the case, okay? Don't get a new calculator the day of your test. Also, that's also a bad idea. Okay. So this is my standard error, 2.445. Okay, so I do 70.3 minus 63.8 plus or minus t star. Oh, t star, we got to go to the t table. What is my t star? 95% confidence. How many degrees of freedom do I have? 12, right? 13 minus 1. I use the smaller between 13 and 15. That's 13, so I got 12 degrees of freedom. So T star, 12 degrees of freedom, 95%, 2.179. Okay, so I got 70.3 minus 63.8 plus or minus 2.179 times 2.445. I've run out of space on this slide here, so I'll copy this over. This is, so far so good with everybody? Okay, great. And so, okay, 70.3, what is this? 70.3 minus 63.8, 6.5. No, I have 6.5 plus or minus, okay, and then 2.179 times 2.445. I have plus or minus 5.33. Okay, so on the low end, I have 6.5 minus 5.33, 1.17, 2, and on the high end, 11.83. Okay, and so I would say something like, I am 95% confident that I'm going to just write golden retrievers weigh on average somewhere between 1.17 pounds and 11.83 pounds more than Labrador retrievers on average. So based on the random samples of data that I collected, we're saying we're 95% confident that golden retrievers weigh on average somewhere between 1.17 and 11.83 pounds more than Labrador retrievers on average. Okay, so the question here, there's a few conclusions that we have to ask is, does our confidence interval provide evidence that golden retrievers weigh more, or we'll say that the mean weight of golden retrievers is higher than the mean weight of Labrador retrievers? And what is our answer there? Okay, the answer here is yes. Okay, what we find is the interval, the confidence interval, is entirely positive. Okay, or another way is the value 0 is not inside the interval. If we did some other breed, okay, or let's say we took another sample and we ended up going from -3 to +6 or something like that, okay? So let's, just, we'll say pretend another confidence interval goes from -3 to +6, okay? And then we ask the same question. Do we have evidence that mu1 is different from mu2, whatever mu1 and mu2 represent, okay? The answer here is no. The value 0 is in the interval, okay? And so that means 0 is a plausible value for the quantity mu1 minus mu2. And thus, we do not have evidence that there is a difference. Okay, we'll end here for today. Have a great weekend, and we'll see you guys on Monday.